Quantum circuits Q sharp. Wait a second. Quantum circuit.
Quantum circuit.
Circuit. That's not Latin. English.
Quantum circuit.
Circuit. Quantum circuit. Then we're going to talk about quantum circuits today. Q sharp, and that looks like okay. Let me switch back to light because those things don't look good. In the dark theme, quantum circuits. Good, quantum circuits. So let's see. What do I know about quantum circuits is that this is the way you basically, this is sort of the graphical way in which you express how do you want to transform your qubits, right? By you usually start with qubits in the state 0, the ground state, because they are the easiest ones to prepare from physical perspective, and then you just with time apply gates here and there, and then make weird things, and then transform your state, and then you do beautiful things which we don't really know what we're doing. But let's see how the Q sharp guys explain that, and let's see what is this. It says it's a 5 minutes read. Okay, let's see. Consider for a moment the unitary transformation C naught 0 1 0 1. I guess that means from bit 0 to qubit 0 to the qubit 1, and then a Hadamard and identity. This gate sequence is of fundamental significance to quantum computing because it creates a maximally entangled 2-qubit state. Okay, so we're talking about entanglement already here, but we really haven't. So what I know about entanglement is that, to me, intuitively, entanglement, based on what I know so far, is that it basically means that you have a bunch of qubits which, by means of applying certain operations, you can correlate to each other, right? So there's a bunch of stuff out there. People talk about spooky actions at a distance, and because the idea is, doesn't matter once you correlate, it doesn't matter how much they are, how much how much far away from each other they are. In theory, the correlation stays there. So we just kind of, I guess, weird from a conceptual perspective. It's not something that you see in nature, right? But the idea is that, so once you have entangled them, and then you can see in this state in here, right? I intuitively read this as in you've got 50% chances of getting 0, 0 and 1, 1, which it means that always, if you read one qubit and you read it and you read a 0, always 100% that the other qubit is going to read a 0 as well, because that's the type of correlation that you've built. That's a type of entanglement that you've done. So that's all I know. But let's see what happens. So, and this is, so this is basically, you see, it's just so awkward to read things like that. That's why the circuits help. Basically, apply a Hadamard first, and then a control knot. So intuitively, what this means to me is always, so on this first qubit, you bring it up to a superposition between 0 and 1, was like 50% 0 and 50% 1, and you make that act as a control beat for a control knot, which literally means that, because it can be both, once you measure, you really don't know at that point, without measuring, what is really, like, it adds, it's like it's adding more, it looks like it's adding more uncertainty, which in turn you could consider as data, right? So you're adding more information in there, or uncertainties. I mean, it just maybe probably sounds weird to call it adding more information, but you're doing something with the Hadamard, which basically means I have the impression intuitively that you have more stuff to process in there, because you basically have you have that uncertainty. So and that's a quantum circuit diagram. The visual language for quantum operations can be more readily digestible than writing down its equivalent matrix once you understand the conventions for expressing a quantum circuit. We review these conventions below. So, conventions. Okay, so this is going to be just, so you have the Hadamard gate. Okay, so top of the line is the qubit reaches 0. and then they are labeled sequentially. So this means this is qubit 0, this is qubit 1. The box with the H is the Hadamard gate, acting on a single qubit. Quantum gates are ordered in chronological order. Left to leftmost gate is the first applied, like this, ABC. But then you have to remember that if you want to jump into, switch to the mathematical realm, you're gonna have to write the multiplication of the matrices like that, CBA. Matrix multiplication obeys the opposite convention, as I say, rightmost. So that's stuff that I know. Multi-qubit circuit diagrams follow similar conventions. We can define a 2-qubit unitary operation B to be HS tensor product X and express the circuit equivalently as this, right? We can also view B as having an action on a single qubit register rather than 2 1-qubit registers, depending on the context in which the circuit is used. Perhaps the most useful property of such abstract circuit diagrams is that they allow complicated quantum algorithms to be described in a high level without having to compile them down to fundamental gates. Okay, guys, what do you mean about that? This means that you can get an intuition about data flow for a large quantum algorithm without needing to understand all the details of each of the subroutines within the algorithm and how they work. The other construct that is built into multi-qubit quantum circuit diagrams is control. The action of a quantum singly controlled gate, where a single qubit's value controls the application of G, can be understood by looking at the following example of a product state input. Okay, this is to say the control gate applies G to the register containing this if and only if the control qubit takes the value 1. In general, we describe such control operations in circuit diagrams as this. Yeah. So you have the black dot and then the actual operation, G in this case. G just being like random thing. So here's the black circle. Denotes a quantum bit. That's what I said. For the special cases where G is X and G is Z, we introduce the following notation. Okay, so the control NOT has its special symbol, and the control Z, okay, that's new to me. For the special cases, we introduce the following notation to describe the control versions of the gates. Note that the control X is the C0 gate. So the control Z this way is the same as the control Z this way, which equals to whatever that means. Q-sharp methods provides methods to automatically generate the controlled version of an operation, which saves the programmer from having to encode these operations. Ah, that's good. Okay, that's good. That's good. Okay, because there is a way, right? So if you take the time to dive into the details, there's a way you can build any control operation by applying a combination of control knots and whatnot. I don't know the specifics, but basically, I mean that's really not needed right now to dive into for us. But the control knot is the sort of the first thing that you learn. But then you can apply control Hadamard, you can apply control to whatever, right? And it's doable. And so Q-sharp helps you by saying that CTL auto-generate the control specification of the operation. Okay, so that basically you can generate the control Hadamard without knowing what gates you have to do, and then you have to put the Q-sharp does it for you, which is pretty good. The remaining operation to visualize in circuit diagrams, because it's just good because that's so if we want to start building up intuition, then those are the useful tools, right? So how do you do a control? It's literally and sort of an equivalent of the if of the conditionals in standard in classical programming and computing, right? So if these, then do that, right? So and it's useful to know that you can just use those. The remaining operations to visualize the circuit diagram is measurement. Measurement takes a qubit register, measures it, and outputs the result in a classical information. Okay, that's just a meter symbol. Q-sharp implements a measure operator for this purpose. See the section and measurements for more information. Okay. Similarly, the sub-circuit gives a classically controlled gate where G is applied, conditioned on the classical control bit being value 1. Okay. Yeah, but that's kind of weird. You see that here, and I mean here I can kind of understand that example from here. So after measuring, based on that outcome, you're still controlling. That's something I hadn't thought of much. I tend to think that the way you build your algorithms is just, you start off, you put the gates, the qubits through the gates, and then you measure everything. But it's definitely interesting. Of course, you can do stuff like that, right? So you read a qubit, and then based on that, you apply and you apply an operation to another qubit. Quantum teleportation is perhaps the best quantum algorithm for illustrating these concepts. Quantum teleportation is a method for moving data within a quantum computer, or even between distant quantum computers in a quantum network, through the use of entanglement and measurement. Yeah, so here moving in that sense, it means you create a correlation, so you know that when those two qubits are going to be measured in a way that it's predictable once you know the value of one of them. Interestingly, it is actually capable of moving a quantum state, say the value in a given qubit, from one qubit to another without even knowing what the qubit value is. This is necessary for the protocol to work according to the laws of quantum mechanics. The quantum teleportation, as we say, if you know what it is, then you've measured it. This means that then you have lost the quantumness of it. So the quantum teleportation circuit is given below. We also provide an annotated version of the circuit to illustrate how we read the quantum circuit. Okay, so that was easy. That was basic stuff. Quantum circuits.